sit on the desk and kick my feet around if you want.
We just missed that introduction.
Okay. Well, for those who are joining us now, that introduction is very profound. R is a massive open source project. There are about 5,500 packages on CRAN, which is just one of the central repositories for R. That means 5,500 different libraries, modules that people have written and said, I want to do something special R doesn't do yet. Here, it's here, everybody else can use that too. It's very, very common in the statistics and applied statistics library that joint was saying, I have a brand new statistical model that I've just developed. I've just proved some things about it, and I have a data set I just ran it on, got an answer. The last little paragraph in that article might be, and of course, I wrote an R package, and it's called this, and you can go do it yourself. So it's a way for people to share ideas pretty seamlessly. The downside to that is that means you have 5,500 different authors who have their own conceptions about what arguments should be, or how the data should be divided, what the structure of the data should be. And often across disciplines, those lines fall. It's true that across disciplines, different disciplines have different languages for what you're doing statistically and what data is called. Okay, so in some places you might talk about covariates. In some disciplines you might talk about right-hand side variables. In some disciplines you might talk about features. These are all sort of interchangeable terms, but they mean the same thing. Sometimes in some data sets, you put your features in one data set and your outcomes in another variable, in another data set. Sometimes you merge them together. So there's a little bit of anarchy to R. What I'll talk about today won't really be affected by that anarchy, because I'm just going to talk about the basic types that are sort of common to the language, the core language that exists without thinking about any library-specific language. And then over the coming weeks, when we add a few more things that are useful as the project develops, I'll start talking about extra things you can do in R, in particular libraries, and those things might start to conflict, right? So the way you call a model in one package might be different from the way you call a model in a different package, or the sort of set of ways you can tweak a graph in one graphical package might be completely different to that in another. But what I'll talk today briefly is just get people up and running as quickly as possible in the pieces of the language that are common to the core of R. I will probably try to shoot for about 40 minutes on R, and then the last 20 minutes on Git and GitHub. And so if I don't know whether Dustin's group is using Git and GitHub. If that's not of use to you guys, then you can take off. Or if you want to sit in on that and then tell Dustin, why aren't we using Git and GitHub? Then I'll be glad to have caused him that grief. So there were some people who wanted to follow along. I'll be running code basically and narrating. So if you want to follow along, and I think that's probably the easiest way to get up and running, you're going to want to have installed R, and not everybody had. So quickest way to do that, if you just put R, just the letter R into Google, it'll come up as the first link because it's R. And it'll be rproject.org. Here's the little page, and there should be a download. For example, I will go through this because, so to download R, it'll ask you to choose a CRAN mirror. There are a lot of different mirrors all over the world that have all of these 5,500 libraries that you might possibly want, and core R. You pick one that's near you. There's not a lot in New England. There used to be one at Harvard, and we shut it down. So there are a couple in Maryland. When you go skim down, people want to go somewhere reasonably close to where we are. So Carnegie Mellon has a mirror, I think it is. Hubley Classifieds in Pittsburgh, Pennsylvania has a mirror that people don't use very often either. It's normally fairly fast. So you want to download R, you want to pick whichever system you've got. If you've got a Linux box, tick that. I'm running OS X here, and some of you will have Windows. It's going to ask you what do you want to download, and I'm just going to download the 3.2 binary. That's the very first link that it offered me, and that's perfectly sufficient for me. Okay, it's going to take a little while to do that. Let's monitor that as that comes in. Ooh, the Wi-Fi is really slow here today. So I've got 3 minutes in which to talk about CRAN. So CRAN is one of the central repositories for R. It holds the R core language itself and a lot of these libraries. Some disciplines have drifted away from CRAN because CRAN has a lot of rules about exactly how your package should look. And it's not just that we can't agree on like what the arguments of functions should look like or how data should be represented, but the rules about what a package can even do. What can it touch on your computer? And what can it do over the internet? Those kinds of rules nobody agrees on either. So there are these other little splinter groups. Big one is called Bioconductor. Most of the people who do genomics data or other sort of med data, all of their stuff split away from CRAN, and they have their own repository system, and there's various other repository systems. We have a repository system here at IQSS that's sort of our own for packages that CRAN doesn't like very much. So when we get to adding in libraries, which is probably the first thing we'll do on Monday, when me and Vivesh share a couple of hours, I'll show you how to pick your repository and how to install a package and how to get extra commands that aren't in the core R function. Everything will be R today. Is everybody who wanted to install R getting the download to come? Is it as slow for everybody? I don't know. What's that?
Mine was really quick.
Okay. I'll probably, I've upset the powers that be enough that they've throttled back my machine, or somebody's sniffing my packets or something. I don't know. All right, so I'm downloading R. Okay, so the next thing we're going to need, though, while we're at it, we'll see how much faster this is. We're going to need some code for today, and this is really not what Dataverse is about, but when you have a hammer, everything looks like a teapot or whatever. So I'm going to. There's two files for us to play around with today. We'll get to one certainly, and maybe the second one. And I've stuck them on our own little Dataverse. So it's a useful time for us to use this Dataverse we've been talking about all of yesterday. This is a test instance of Dataverse. This is not the real Dataverse. I wouldn't throw junk up on the real Dataverse and archive it for all time in posterity. So Dataverse Demo is a version of Dataverse that's sort of for people who are developing apps and want to throw nonsense on it and just see how badly nonsense corrupts it. And so go to this address, and we can play with Dataverse while we're at it. iq.harvard.edu. Probably can't spell Harvard. And if you go there, you will see, let's see, oops. Here's Dataverse 4. Oops, where is it? It should be vaguely in order of whenever I just uploaded it. Yes, somewhere on the front page, and if you don't see it on the front page, you can search for it. There is a Dataverse called PUMS Data California. This is data coming out of the census. It's a data set that we've used a lot in this project as an example of data that is very much in the style of private data, even though it's publicly available. It is a subsample of actual census responses. So the census collects a lot of private information from every single person in the United States, or everybody they can contact at least. What they do is they make some of the individual level data publicly available, only a few variables, and they do a subsample. So so not everybody's in there. This is a 5% subsample. So 5% of California is in the California version of that, but that's several million observations. And the nice thing about that is that's a really large data set for us to test our algorithms and see, do they work at 500, do they work at 1 million? So we'll play around with this as sort of a standard reference data set here and there. So if you click on this Dataverse, in there you will find, here are some of the versions of that data set. Here's a very small extract of it that only has 2,000 observations, it says. PUMS 5 small. Does everybody only see those 3 things?
Yeah.
Well, if you click Explore, you'll pull up the nice little Two Ravens app, but that's not actually what I'm looking for. In theory, it should be that our code should be up here. Let's just take a look at where it's gone. it might have you built this server. Files.
Should we log in with that help?
No, because I am knows who I am. Let's see if I just need to publish some stuff. 1 second. It might be that I uploaded the files and didn't publish them. I see them there. Okay, it's thinking about it, it's thinking about it, it's thinking about it. I uploaded some data sets. Apparently I didn't tell it to make them publicly available. Okay, how about reloading this and see whether that crashes Dataverse. If we go back to PUM's Dataverse, it's thinking about it. Oh, everybody's going there at the same time, so it's slow. Okay, do people see extra files there now? There should be a hello.r and a dpqr.r if you want to download those files. How many people are looking for those and not seeing it? dpqr.r. Oh, good? Okay, great. So download those somewhere. And I'm going to suggest you don't download them onto the desktop. You can put them wherever you want, but we're going to need to know exactly the file path to where we're going. Okay, so it might be best if you're building it. Again, this is going to be dependent on what operating system you have on your machine. But maybe go construct some folder somewhere. So if you're doing Windows, go into your C drive. And build something like if you've got somewhere where you hold things, my files / build a folder called privacy. Or if you're in Linux, OS X world, you might go into somewhere like /volumes. If you've partitioned your drive, I've got a drive partition here. I think I called it Scratch, or whatever you've done. My files. It's probably under volumes though, and then create some folder called privacy. If you're in desktop, if you have to throw it to the desktop because you don't know any of the drive paths, we'll work something out for you. But I'm guessing everybody can put something into a folder somewhere on their machine. If that is not a correct, if that's not true. Let me know, and I'll think about. Does anybody know what the desktop paths are in Windows or Mac? Does anybody need? Well, no.
No, it just says desktop.
It's just like /desktop.
That's the
It might.
address, yeah. I don't think I even have to see.
Okay. Well.
It starts at volumes, and then sometimes if you have a different drive and users, then your username, then desktop.
Yeah. So something. Okay. I'm gonna go. So I've downloaded R. I'm gonna go to in OS X world. I'm gonna go to my downloads. It's a nice little package here, 3.2.0. I'm gonna double click it. It's gonna give me an install routine in off Windows. It's gonna be a similar thing. You're gonna see a little install zip that you've probably downloaded, an executable. You double click on it. Probably it's on your desktop, and then it asks you to install. So I'm gonna install. I'm sure we've installed things. I am going to agree, it's perfectly fine. I want to why is he asking me these things? Oops, continue. Sure, why not? Scratch. Oh, I haven't updated my OS X. That's okay, because I already have R on my machine, so I'm not really going to worry about that. But it's chastising me for not having updated my OS X, my operating system. Okay, so when you've installed it, if you install it successfully, I have very little screen space here. R might appear on your desktop if you put a shortcut there, or it will appear in your applications. The first time you click on it, it'll say, are you really sure you want to open R? Because you just downloaded that off the internet, and the internet can be crazy, and we just say that's perfectly fine. Okay, so you'll get, if you open it up in R, we'll talk about some of the other ways of looking at R maybe in future weeks. So for example, lots of people prefer to use RStudio, which is which is an interface that allows you to call R, but also has lots of other windows open. It's an IDE for those of you who are familiar with environments for programming, although it's not really much of an IDE. If you just click on R though, this is what you'll get. Very old-fashioned sort of prompt. A little caret there, it's waiting for you to type something. So let's find out where it is. The first thing we want to touch is, the first command we want to give it is get WD, and here's a logic to R. Absolutely anything you can do in R is a function. Okay, so even if it's a function that has no arguments. So parentheses are going to come after the end of a function name. So this is a function that's going to tell me get the working directory. Okay, in like if you're a Linux or a Mac user, this is like PWD, for example, finding the root path right now. So get WD is going to get the working directory. This is in the crib sheet if you take a look. I just want to see where I am, because I'm almost certainly not where I want to be. So again, everything is a function. Either in looking at data, opening up tables, creating plots, even quitting out of R is a function. Yeah.
Are there any spare sheets?
Yeah, there's some at the front here. So
Sorry to interrupt.
they'll make their way around.
Appreciate
So it's telling me I am in /user/J Honaker. Now, so I could put those folders, those hello.r and that dpqr, into that path if I can go find it, and then it'll find the files. It's always going to be looking for extra source code in the local working directory. But I'm not going to be that lazy. If you know where that path is, go ahead and put the hello.r and the dpqr into that path, and then everything will be fine. I already know where I put these files, so I'm going to change my working directory. I'm going to set the working directory, setwd, and let's see, just for a moment. Never mind. This is all one line then, and then I'm going to give it a path in quotes. So for me, it's going to be /volumes/ whatever it is in my particular case. Close the quotes, close the parenthesis, and see if you can get somewhere. So I'll show you. Is this big enough for everybody, or do you need bigger screens? We're good. I'm going to set my working directory to, I know I'm going to volumes, scratch, classes, privacy, R. This is the folder structure that I already built. And if I want to check to make sure that the files that I downloaded are already there, dir will give me a directory listing. And it's going to tell me everything that's sitting in this folder for me. So I have got my little crib sheet PDF that I dropped into this folder. I've got my 2 little pieces of R code. I've got some LaTeX intermediate files that are just noise. It's just telling me what's in that folder. So I'm in the right place. I've got my little piece of code here. Everybody who wants to get to this point at this point. If not, I'm trying to think. Someone who knows R could maybe come around and help people who want a little bit of assistance.
Mine says I can't change my working directory.
Ah, okay. So if you try something like set working directory, volumes, this does not exist, and I'll just tell you that this does not exist as a folder that doesn't exist on my machine, it'll give you an error message like that. So that just means that somehow it has not found that folder structure that you've looked for. So either maybe there's a spelling error in there, or there's a slash that's wrong, or there's a backslash instead of a forward slash. Also, it doesn't like spaces and strange characters that normal folder structures will ignore. Yeah.
It also doesn't like having the volume name at the start. I had that problem at first. Getting rid of
Volumes?
Like, yeah, I just.
Yeah, that's just the sorry. That's the way I mounted my drive onto OS X. And if you put it somewhere else, that might not be your first folder.
Can you use like dot period to change directory from the current directory you're in?
No, unfortunately. You can access files that way normally when you need to read files. So we'll see some sourcing and some reading, and you can reference things with respect to your current directory, but you can't just back up in the set working directory folder. Did it work for you? Splendid. Great. Okay, so I'm where I want to be. If I want to run a command, and this is probably the last time I'll put anything up on the board, because from this point on, I'll be able to look at my code. I'm going to say source, and then in quotes the name of the file that I want to run. So it's source, and in this case I'm going to run hello.r. Depending on your machine, it may be case sensitive. Okay, so the file itself is a lowercase r. It's going to depend on your system properties as to whether or not it pays attention to that. So I'm going to run hello world.r. It's going to give you an error message. This error message is not really an error message. It's just the message is given when the code itself has a stop command in it that says don't compile beyond this. Then that seems like an error. It has an evaluation that it can't get beyond, but intentionally so. If you got this little message, hello world, then you ran your first little R program, or the first R program of this hour. And there's our classic little get your language to print hello world to the world. Everybody got this up and running who was expecting it to get up and running? Yes?
It actually said hello.r wasn't found, but with jitter parentheses, it
Yes.
said it was there.
So when you did this, you see it,
I've got it.
and when you sourced, it went away.
Oh, I see the issue. Okay. Also,
Okay.
thanks.
Maybe I'm guessing a couple of things to keep in mind that always trip me up: case sensitivity and quotes.
Yeah.
Okay. So if you can open up that directory, let's just take a look at the actual piece of code, and we'll walk through the code and then see how it was sourced in at the prompt. Okay. I'm going to open mine up in. If you've got different people that got editors that they like. I generally use an editor you can download if you don't have an editor on your machine called Sublime. It's reasonably good about understanding R code by default and also LaTeX code if you create your documents that way. But it's nothing special. It's not going to do a lot for you. It's not going to compile. It's not going to find bugs in your code. It's not an IDE. That's what RStudio will do. I'll point you to RStudio on Monday perhaps, but I won't generally use it myself. Okay, so you can open up the code in anything you want. If you double click on it, it says it doesn't know how to open that file. Open it up in Notepad or open it up in whatever way, any text editor you particularly like, WordPad if you're on Microsoft. Just anything that opens up ASCII files. It is just an ASCII file, and the .r is reminding us that it's an R file. R itself doesn't care. If the extension was .nonsense and you said source something .nonsense, it would go find that file and treat it as if it was R. Okay. So it's just a convention that we name these things .r so we can find them, and it's not a convention as to whether that R is upper or lowercase. But hey, R is a little bit of anarchy. So here is our very first program. It's going to compile. It's going to run each of these lines until it doesn't know how to run a line. Okay, so R is really a very simple language. We'll talk about all the different ways in which it is simple, and we'll realize that however simple you think it might be right now, it's probably simpler. It's going to execute each of these lines as if it's just reading down a script. So R is really a scripting language more than a high-level language. It's just going to execute each line until something trips it up. Okay. The comment character is the £. Okay, and so one of the reasons I'm going to use Sublime is everything's color-coded, make it a little bit more obvious to you what's code and what isn't. Reasonable, simple coding practice that we'll try and adhere to is to give every file a header. Okay, so at the top of the files, we're going to comment out a few lines and tell ourselves what this piece of code is trying to do. So here's what I believe the name of the file to be. It's hello.r. I'm going to give myself a one-line description of what this code is doing. It's going to demonstrate some screen output. And I'm going to put physically into the header the last time I touched the file and my initials. And this is reasonable coding practice for the following reason. It's going to be the case that as we're writing lots and lots of files and as we're running them on different machines and on clusters, they'll drift. And the last time you saved the document on your machine, which will tell you, which in your folder will say, the last time that file was saved, might not really be the last time you made a significant modification to it. And so just looking at that will not tell you if I've got multiple versions of the same piece of code across different computers or in different folders, which one is actually my most recent. Okay, so changing the date every time you made a major update is reasonable coding practice for keeping things up to date. And we'll also rely on some more advanced tools, like we'll talk about GitHub in a little while, for really keeping the code base up to date. But when you've got a lot of personal code that you're not going to be sharing, this is just a way you're going to have multiple versions of the same code proliferating. You're going to save some into your email. You're going to save some onto a USB drive or something. And you're going to end up, if you ever try to go back to a piece of code that you haven't been using that week, you're going to have forgotten which version was the one you wanted. So try to keep your dates up to date. Also try to keep these things up to date. Just give yourself a 1 or 2 line description of what this code was trying to do, because you're going to forget, right? If you're going to, a couple of weeks from now, say, you know, I want to draw a plot, and this plot's going to look just like a plot I did 2 weeks ago for this other algorithm. I'd love to recycle some of the plotting commands, and I just cannot find that thing. So if you keep some descriptions that are reasonably straightforward, that might clue you in on that. Obviously, you can include lots of good comments in your code, but it's easier to read the headers than it is to work through 20 or 30 different files until you find the comment that you're looking for. And if you're sharing code across people, adding your initials, as I was the last person who touched this, might give you some sense of, do I have the right version? Do I have the version that was changed most recently and by me? If we're swapping code across people. So keeping your headers up to date is just good coding practice if you are building multiple different files and think you might ever have to get back to older files. Okay. And then doesn't matter how many pound symbols there are. R does not have a line delimiter. You'll notice, well, it does, but R fundamentally assumes, if you want to have a philosophy about what's going on, what R is thinking when it's executing your scripts. R is kind of assuming that you are incredibly smart and incredibly lazy. Okay, so you can make a lot of mistakes in your R code, and R will say, I'm sure that person intended to do that. Let me try to work out what it was they were trying to do. Okay, so there are line delimiters, but if you don't use them, it will ignore that, and it's actually pretty much convention to ignore the line delimiters, the way of saying this line has just ended. So unless you need to put multiple lines onto the same line, which occasionally you do, we're going to ignore line delimiters. So R basically lets you be pretty sloppy and assumes that you're intentionally being sloppy because you're so smart. Okay. It's also not good to anthropomorphize computer languages, right? But they hate that. But we'll speak of R's if it's an adversary sometimes. Okay, so everything after a pound symbol is a quote. There is a comment. We don't turn off comments afterwards. So most other languages, there might be multiple ways of creating comments, both to enter a comment and to leave a comment. We'll just use the pound symbol, and everything after that is a comment. If I need multiple symbols, multiple lines in my comment, I'll have to start multiple lines with the pound symbol. So this is, again, it's just a comment, and it's just telling me, okay, this is a section in which I'm going to be doing some printing. What am I going to do? I'm going to run my first function. Everything in R is a function. So there's a function called print. It's going to need an argument, and in this case, the argument is a string. Strings in R are in quotes, and it says "Hello World." What did it do? It printed "Hello World" to my string. Okay, so it ran that line and it just keeps reading down until it comes to an error. The next function it runs is called stop function. It says, "Oh, what should I do with the stop function?" Everything's a function, so I'm going to expect parentheses. There's no argument though. There's nothing I need to give the stop function in order for it to work. And stop terminates. Stop tells R, stop reading this script anymore. Don't do anything. So if I want to continue. Here we can edit our code. I'm going to just delete that little stop command, or maybe the whole, oops, not the whole thing. Delete that little stop command. I'm going to save it, and then I'm going to run it one more time in R. I'm going to source it in, and I might have it open in a place that's different. So let me just close this and open it one more time. I have multiple versions of that code in different places, so give me 1 second. Oops. So here's Xcode, which is also a reasonable editor, and color codes too, but I'm going to open it up one more time in Sublime. And yep, I was editing it at a different location, so now I'm going to save it, and I'm going to run it one more time, and it's going to continue. Okay, so it did a bunch of other things. All right. What's the first thing to see here? is that R is really a scripting language. It's not a high-level language. So it has a couple of things that, again, it's going to assume that you're really, really smart but really, really lazy. And at the heart of that, something that will bite you eventually is the fact that it is loosely typed. Okay, so I do not need to describe, as I do in most languages, the types of the objects that I'm going to create. Normally we do that in a language. We say, I'm going to construct some things, and they're going to be matrices and some other things, and they're going to be vectors. And then the compiler, knowing that ahead of time, is going to make sure you don't do the wrong things to the wrong types of objects. And it's going to reserve memory very intelligently for those objects. It's going to say, oh, it's a vector. Well, you're not going to need much memory for that. Oh, this could be a giant file. You'll need a lot of memory for that. R is not going to think about types. Hidden behind R, almost everything is being stored as a double. Okay, so everything. So even though things look like strings to me, and we'll see lots of other things are going to basically be stored as large arrays of doubles. So that means since everything is basically stored the same way, it's very memory inefficient. R is a terrible memory hog. That's another reason we often, in production, move things out of R into other non-interpreted languages that are better. But for us, getting up and running, not having to deal with types, does let us do things fast. It also can bite us, though, because it means we can accidentally change the types of things all the time. We can do it intentionally if it's useful. We can do it unintentionally, and it can often wreck our code. Okay, so what am I going to do? The first thing I'm going to do is construct a matrix. Matrix is probably one of the two basic types that exist in R that we're going to use very commonly. Constructing a matrix, everything's a function. So if I want to build a new matrix, this arrow, that's less than sign dash, that's assignment in R. Right? So this is saying I'm going to construct a new object H if I want to read this. And what am I going to put into H? I'm going to assign it. Sometimes you use other symbols like equals in other languages. Whatever comes out of this function called matrix. And the function matrix is a base to R, and it's going to build a matrix. And matrix needs to know some things. It needs to know 3 arguments. One of them is called n, how many rows? The first is what are you going to put in my matrix? The second is how many rows and how many columns would you like in your matrix? Okay. If you don't know what the arguments are to your function, some of your editors will tell you. So if RStudio, for example, as you start to type the function, will remind you what the arguments are to that function. Or here's help. Help is a function in R, just like everything else. Help. And I could say, give me some help about this thing I'm going to create called matrix. And you'll see a very quick help. Here's the function, here's its usage, here are its arguments. So you fill it with data, you tell it how many rows you have, you tell it how many columns you have, and then it's got some other arguments. And if you don't tell them the arguments in help, then these are going to be the baseline definitions that you haven't changed. All right, so if I hadn't told it how many rows, it was going to give me a 1-row matrix. If I hadn't told it how many columns I wanted, it was going to give me a 1-column matrix. We'll play with functions in a little bit more detail if we get to the end of this example today. Okay, so help's useful for defining things. I don't need to name things in my argument, and I've done that intentionally here. So I did not name data. I did name n-row and n-column. Okay, so if I name things that are arguments in my function construction, then it will find any argument in matrix that's called n-call and set it equal to 2. Okay, and if I name things, I do not need to put the arguments into the function in the right order. Again, you can't get away with that in a lot of languages, but R says, you're lazy and you're smart, you meant to do that. Okay, so if you name things but you put them in the wrong order, R will be perfectly fine with that. It'll just match the names across the arguments. If you don't name them, you'd better get the order right. So here, for example, I didn't name my first argument, so it's going to take the first argument that's required for matrix, which happens to be data, and say, okay, well then data is equal to 1. Okay, so here's a little bit of sloppiness on my part. Okay, when you're starting off, I would absolutely encourage you to name every single one of your arguments. It'll just teach you the ordering of the names and the functions that you use commonly. It'll make your code more readable as we pass it off across individuals. Okay, next function I want to do is print h, because I wanted to see what I just constructed. Okay, then on my next line, I'm going to do the following. I'm going to say, H is assigned to be hello world. So here is an example of loose typing in R. I just constructed a thing called H that had type matrix. And then 2 lines later, I said, oh wait, forget that. It's not a matrix anymore, now it's a string. And it just had its type recast, as we'd say in CS. It's been changed from a type matrix to a type string. R doesn't care at all, okay? Underneath R, everything is doubles or arrays of doubles anyway. So now it just says, oh, that's a crazy double in a 1-by-1 array. It doesn't really matter. But this will bite you, okay? So you know, if you use the same name multiple times in your code, and you can and even if they're very, very different types, you can accidentally overwrite things you were relying on existing later on, okay? Also, some functions will, if they return a type that you didn't expect, you might never know it, right? So you might be working on some matrix called H, and then you get some function that you perform on H, and it overwrites H, and you assume it's just going to be a matrix again, and it turns out that that function gave you a vector. You're never going to know, because in another language it would say, oh, there's a compile error here, I got back a type I wasn't expecting. Ours is going to say, oh, you wanted to change the type, obviously, you're a vector now, okay? So we can do this, okay? We've just converted a matrix into a string, recast it as a string, print it again and stop. Okay, so there's an example of what's called loose typing in R. Again, what it means is you don't have to define at the beginning of your code all your different objects, what types they're going to be, how much memory you need them to be, what size you want your arrays to be. It makes it very, very fast to get up and running. It also means that because you don't have control over those base kinds of things, that R might not be very efficient, or it might trip you up later on when you're relying on that kind of structure. Okay, so get rid of that second step comment, save your code again. Let's take a look at what we're going to do next. Next, we're going to build some other types. So the first thing I'm going to do is I'm going to build a sequence. Here's a quick notation for a sequence. This is going to be a vector that goes from 1 to 15. So I'm going to create a new object called S. I'm going to assign to it the vector that comes out of this 1 to 15. Okay, so this is some of the notation in R, some of the operators that exist in R, like plus, minus, divide by. You're probably familiar with this little colon here constructs a sequence. Okay, a little operator there. So it's going to print out S, so that should look like a vector from 1 to 15. I'm going to rebuild my matrix. I'm going to fill it with S. That's my vector of 1 to 15. That's my data now. And I'm going to have 5 rows and 3 columns. So let's see how a matrix is constructed when we do that. Oops, don't want to help again. I want to run the code again. Source. Okay. So we went through our code. Again, it executed all those things at the top of the code that I didn't cut out. Here's S. It's from 1 to 15. You'll notice that when you print something out, when you print and you don't tell it anything, well, R thinks everything is an array. Okay, even though there's all these crazy types, it's storing it as an array. So everything you print, this first little symbol here, that's the row number of the array. So I constructed a vector that went from 1 to 15, and it saved that vector as an element in the first row of an array. If you don't want that 1 to be there, there are other print statements that are a little cleaner, nicer looking to the eye, like CAT instead of print, cat. Give you a little more control over what print looks like, but we'll stick with print for right now. Okay, so first I printed S, that's from 1 to 15, and it's just this 1-row array. Then I constructed a new matrix H, and I filled it in with S, and you'll see what happened here. So here is the new H. It's got 3 columns and 5 rows like I asked for, and I filled it up with the vector from 1 to 15, and you'll notice that it populated it by column. Okay, so you might think that it would populate it by row, as some languages will fill in arrays. R is going to populate by column. If you wanted to populate it by row, there's an argument in matrix that you could have swapped off if you look back at that help for matrix. If there's a by row is equal to true or something like that, you turn it to false and it would populate it by row. Okay? It will recycle. So if I had said instead H is equal to a matrix, fill it up with S, and my number of rows now is going to be 6, and my number of columns is going to be 3. Okay, it's going to give me a warning message. It's going to say, you know, are you sure you want to do that? You don't actually have enough pieces to fill in the matrix. You only have 15 objects in this vector. You've just constructed a 6 by 3, 18 size matrix. I'll give you a little warning. Okay, so R will occasionally say, you know, I know you're lazy, but are you that lazy? But it'll still do it. So here's H. What has it done? It's filled it in by 15 and said, oh, you ran out of things. You probably meant to do that. Okay, I'll start recycling. Okay, so code that when you make errors, often R will come up with some sort of, this is probably what you meant, and not crash. And that can be really infuriating because it will mean that your code should have crashed to tell you did something wrong. It doesn't crash, and then you look at your answers and go, what's going on here? Well, it might not be the last thing you did. It might be something you did very, very early on. So as you're building your code, until you get familiar with R, I would encourage you to build in small packets, build line at a time, and give yourself lots of screen output to make sure that the things that you construct are exactly the things that you expected them to be. Put in lots of print statements. Watch the things as they get constructed. Again, there's not really a very good IDE. Like in other languages, you might have another window that shows you everything that exists in memory. Now, all these things do exist in memory. If I want to know what's in memory, ls is a useful command. That'll tell me what I've constructed that exists. And it'll say, you've built something so far called h and s, and I could print those things. I could print s again. I could print h, like we've been doing. And that's useful. But you might want to put these print statements, sprinkle them throughout your code, because obviously that's just the most recent version of h. It's not what h was earlier in my code. We are going now with some rapidity, but are there any questions so far? Yeah.
Yeah, for matrix, and then you did parentheses s, could you have just put 1 to 15, or?
Yeah, so I could have I could shut down my machine, or I could have done that. That would have been fine. I could have done, 1 to 25, and it wouldn't have used that whole sequence and said, you probably didn't want the rest of them, and it just truncated them.
And it would have done the same thing it just did with reassigning?
If I have more elements than could fit the matrix, the last elements would just never make it into the matrix. Yep. So I could fill that up as I like. Okay, I'll get rid of that little stop command. Just to clean up my screen output. No, I'm not going to do that, because I might need some of these things later. Okay, so I'm going to pull out that stop command. I'm going to run a few more pieces of code as we continue. What's key on the rest of this code? Sequence is it gives you a little bit more control if you want to construct vectors, right? So colon assumes that you want to construct a sequence and you're just adding integers. Sequence will let you build sequences however you want. So from a starting position, so I could start at 1, increment by 3, and make a sequence that's of length 5, for example. That t is going to be 1 plus 3 is 4, plus 3 is 7, continue and continue until I get a vector of length 5. That gives me a little more flexibility than the colon did. And then I'm going to construct a different type in R. Again, I can always change types, but a very useful type in R is the Boolean. So Booleans can only take true, that's true in capital letters fully spelled out, not t, or false, capital letters fully spelled out. F and T are occasionally used as shortcuts, but they aren't quite the same. They don't have quite exactly the same meaning in R as true and false. F and T are actually shortcuts that point to true and false values and aren't always reliable. So I wouldn't start off that way. So let's take a look at what we're going to do is we're going to construct this sequence. 1, 4, 7, and so on and so forth. And then I'm going to run a little function over here. I'm going to use a function called round. I'm going to divide t by 2. And I'm going to say, is whatever number comes out of the rounding equal to t over 2? Double equal sign is my operator, which says, is it equal to? That's the test indicator. That's either true or false. Okay, so single equals is going to be used for arguments inside functions. Okay, assignment is going to be used for setting a value that I've just constructed, and double equals is a logical operator, which is either true or false. These two things are equal or they're not equal. Okay. So this is a little operator saying, is the vector that comes out of here equal to the vector over here? This is going to be true if it's even. It's going to be false if it's not, right? Because it will have rounded. Yes.
So from using R, it doesn't really matter if you use assignment or equality, or does it?
I'm sorry?
It doesn't really matter if you use the assignment or equality. Like t equals sequence would still make.
Yes. Okay, so it is absolutely true that as a shortcut, you can use the equality symbol for the assignment symbol. It's not considered good convention, but it'll work. It's absolutely true. So for reading code purposes and just for accepted modern convention, we'll use assignment. But it is true that you can sneak equality in on the left-hand side as the assignment operator. You cannot take the assignment operator and use it for the argument operator. So you'll end up confusing yourself. It's useful to keep them distinct, and I think that's why the convention changed. All right, so let's run this. I'm going to do two useful things. First, I'm going to print out flag. Flag is just a flag, a vector of Booleans. They're either true or false. And then we're going to start subsetting, and let's see what happens. So source my code one more time now that I've saved it. Oh, if you don't know this, you might keep printing in, typing in source, but the up arrow and the down arrow will let you toggle at the command prompt between things that you've already typed in. So I'm just up arrowing until I find source again and pressing it. And again, I get that error, but it doesn't matter. It just means I got to a stop command. Okay, so let me think about all these things we constructed before. Here is my vector of 1, that was false. 1 was not even. 4 was even, so that statement was true. False, true, false. So I get a little vector of Booleans. Booleans are particularly useful for managing data. Okay, so if I want to construct a query on a data set, if I only want the observations that are in California, or I only want the observations that are males, what I can construct is a vector of trues and falses. Say, does this meet my query or does it not meet? Is it in my set or is it not in my set? And then this thing can be used to subset a matrix. Okay, so I have done that in this code. Let's look at that. I'm going to print, this is my vector of trues and falses. And then this hard bracket, that's how I construct a subset. T is my sequence. Let's take a look at my, follow along with the code while I do it on the screen. Here's T, that's my sequence, 1, 4, 7, 10, 13. Here's flag, okay, not even, even, not even, even, not even. And then here's how we subset, T, hard parentheses, hard brackets, angular brackets, square brackets, whatever you prefer to call these. Hard brackets. If I put my Boolean vector inside this, it's going to take the observations of T where this flag is true and ignore the observations where it's false. So it's not going to take the first observation. It will take the second, won't take the third, will take the fourth, won't take the fifth. And so that is just 4 and 10, the second and fourth position in that matrix. Okay, and that's a very, very useful way of manipulating data here, and that is that's very useful in not a lot of languages have Boolean subsetting. Okay, so so you can construct a sequence. You can say I just want the observations that are greater than 6. Okay, so build a flag. Is that variable greater than 6? Then pull out just the observations that have that for which that is true. Okay, all right. We'll do some more on subsetting while we're at it. Okay. You can also subset in those parentheses by numbers. Okay, so here's another subset. I'm going to go to the matrix. So a vector has just like the vector like T that we constructed. T just has one dimension, so you just put in trues and falses. We could have also subsetted by numbers. So if I had said T3, that would have given me the third element of T. If I had said T3, if I'd stop doing that, please. If I'd said T3 colon 5, we know that the colon operator gives me a sequence. So this is 3, 4, 5. That's going to ask for the third, fourth, and fifth elements of T. If I've got matrices now, like H, that we've also built, that had rows and columns, I can subset on rows, and then I have to tell it which columns I want. So that's a 2. That would say I want the third, fourth, and fifth rows, and the second column of the H matrix. And that will give me a subset. Okay? If I ignore one of my indicators, that means I want all of the columns. Okay, like DIT in some other languages. Okay, so here what have I said? I want the second through the fourth row and the third column of the H matrix. Please print that. That'll give me a submatrix. All right? structure in R. We'll come back to probably in the future. There's loops are fairly simple. There's two types of loops. The other type is in the crib sheet, but the one that we use most commonly is just a simple for structure. This is going to say, okay, I'm going to execute the code inside my for loop as many times as the loop is called. All right. What am I going to do? Inside my parentheses, everything in R is a function. So there are not too many times that I cannot say that too many times. Everything in R is a function, including the loop itself. The loop itself is a function. Okay, so a function has arguments. The arguments look a little bit different, but in this particular case, the arguments are what am I going to increment? I'm going to create a counter called I, and for all of the possible values of I in whatever the sequence is on the right, so that's a sequence 1, 2, 3, 4, 5, execute this code. And everything that's inside the curly braces here is going to be run. It's going to be run once when I is equal to 1, then I is going to be incremented to 2 and run again, and incremented to 3. So in this particular case, what's going to happen? The first time I go through this loop, I is going to be equal to 1. I'm going to make that print statement. It's going to say the next element of t is. Then it's going to print the first element of t. T is this vector that we've got trailing around. And then it's going to do something. Okay, this is going to set something equal to true. Second time I do this, I is going to be equal to 2. So it's going to say the next element of t is, and it's going to find the second element of t and print that out. It's also going to do this thing. Okay, so you're going to do this 5 times. Then when it's finally gotten through the counter, it's going to be done. Any questions about looping? Well, we'll come back to looping. We can make loops much more complicated than this, but this will get us up and running. Looping sort of an important structure that you want to build. It looks a lot like looping in almost any other language. Any other questions about looping? The only strange thing for those of you who've seen looping in other languages before, why do I care about, why do I have this? Anybody want to tell me why it's interesting that if I set this exists equals to true inside the for loop and then ask what it is, when I run this code, let's see what happens. This is really quite an aside, but it's worth starting to think about in R. I source in my code. Here was the loop. The first time I went through, it said it made that print statement, printed the first element of t, then the second element of t, then the third. And then finally, when I got out of the loop, inside the loop, every single time I went through the loop, I constructed this thing called this exists and set it equal to true. And then I said, what does this exist? It's true. You said it 5 times. You know, why is that interesting?
The scope is global.
The scope is global. So normally, in many languages, loops have their own scope. Okay, so things that are constructed inside the loop do not exist when you exit them. Things that have not been, or in some languages, until you've constructed something, you can't reference it inside the loop. But here, there's the scoping is global. That is, you can build things inside the loop if they, and they'll continue to exist out. The loop function, also the if function, behaves in the same way. Does not have its own scope. That means that when the loop closes or the if statement closes, the things that you constructed are not destroyed in memory. Okay? So what does that mean? That means probably some of you are saying that means you can be really lazy, and that will bite you, not in R, but when you go back to a language that doesn't have that, and you're like, well, why can't it find these things that I constructed in my loops? So that's that. We'll talk about functions probably. Yeah, I'll talk about functions today. I guess we're actually doing all right for time. We'll run on by maybe 5 minutes. Let's run on. Functions are constructed in much the same way. Everything in R is a function, but obviously I can construct my own functions. Did I kill my last stop statement? I didn't. I'm just going to delete that. Okay, so here's my function. If I want to build a function in R, it's a lot to talk about in functions. There's a lot of little R function quirks. So I'm going to, which I want to point out. So I'm going to skip functions until we come back to R on Monday, because we won't need it for the things that, Kobe's going to give you some assignments on Friday that he wants you to start playing with. Obviously some of you are going to want to get up and running on your own projects as well. But I think you can probably survive without writing your own functions for the time being. So we'll come back to the quirks of functions on Monday. Let's get to, let me skip functions. You'll see the screen output, obviously, but let's talk about data frames and lists, and then we'll probably be in good shape. Okay, so we've seen matrices. Matrices are rectangular arrays where every value inside the array needs to be a number. I cannot put these booleans that I've seen, for example, inside a matrix. A matrix only takes numbers. Everything in, remember, everything in R is being stored as doubles. So some of you might be going, wait, when you put a number in an array, is it an integer? Is it a real? Is it a double? Is it a float? Everything's a double. Okay, so not only do we have loose typing, but we don't even have like types of numbers. Everything's a double. Okay, so it might be printed to the screen and rounded for you, but it's a double in memory. So again, it's going to steal a lot of memory. Okay, matrices can only take numbers. Basically, there is a number type, and all numbers are just going to be treated as doubles. If you want something that's more flexible than that, and most data sets have got lots of different types of variables in them, we're going to construct another object called a data frame, which is slightly more unique to R. Yeah.
Are Booleans doubles?
Yes, in memory, although that's not how they're being treated on the screen. So you might think, so here's the thing, if you're trying to write good, if you've been taught how to be a good programmer and you're being efficient and you're saying, you know, this variable doesn't have a lot of information in it, it's only binary, I should store it as Booleans because then my memory usage will go down. Well, no, because in the back end it's being stored as doubles and you've just caused yourself more work. So Booleans are useful because they're easy to read and you can subset by them. But don't go ahead, don't start converting things to Booleans to save memory because it's not doing anything for you. Yeah, even Booleans are doubles in memory, the way they're, because that way R can change types very easily and not have to readdress the memory, right? If it turns it into a vector, well, it already had reserved memory for a vector, so it doesn't matter. Okay, so here's data frames. Data frames are like matrices, they have rows and they have columns. Okay, but I can store different types in each column. Okay, so each column should have the same type, but I can have different types inside my columns. So I'm going to start building some fakey data. Okay, I'm going to set some parameters. For those of you who might be doing Monte Carlo simulations, here's an example of building some fake data that you might want to test your algorithms on. I'm going to construct M. I'm going to assign it to be 20, so that's just an integer. Again, really, it's an array of doubles in R. I'm going to construct A. I'm going to use this function called rep, which is repeat. I'm going to repeat true, false, n over 2 times. So I'm going to get 10 true, false, true, false, true, false, true, false, where that little C is also a function, and that means concatenate. If I want to build a vector and I want a quick notation for it, C is incredibly useful. It will sneak into your code all the time. That means, so that is just the vector true and false concatenated into 2 things. Okay? So A is going to be a length of 20. It's going to be true, false, true, false, true, false. X is going to be, here's our first simulation from a distribution. Okay? And this is what R is built for doing, right? Building, allow us to write things down in the style that we would use if we were statisticians. So if I got a bunch of equations on a page, the nice thing about sort of the R language and the way it's written and the way we have assignments, and we'll talk later about the way that it's fundamentally a functional programming language, is that you can write things down, equations that appear on the page you can write down in R and then they will do the same kinds of things. So what I'm going to say here is, I want to create a variable x that has some random draws from a distribution. Well, there's a function for creating random draws. There's a convention that, distributions, if my distribution name is dist, okay, then there are 4 ways of accessing the distribution. D, P, Q, and R. And I have a separate piece of code that you can run, which will be useful for seeing plots, dpqr.r, which will show you the differences between these distributions. Okay? And there are 4 different ways of accessing the distribution. We normally, it's easy to say, well, there's just a distribution. It's a normal. You can judge how many statistics classes somebody has taken by how nice their normal distribution looks on the blackboard, right? I've taken 2 apparently. And so R is to take random draws from the distribution. Here's the distribution. Give me some random numbers that if I took enough of them and created a histogram would have this distribution. Okay? D is saying, what is the height of this distribution? What is the density function? at different values along a parameter. Okay. P is going to tell me what's the integral of the distribution function. What's the sum of all of the area as I get up to some point. Okay. And Q is the inverse of the cumulative function, which is the inverse of the integral, which we'll see later is very useful if you want to take random draws yourself. But we already have this function R, which is going to give you random draws. So if you want random draws from the distribution, you're going to use, say, R, the distribution name. If you want to know what's the probability of seeing some value in a distribution, you're going to use the density function. And if you want to know what the integral up to a point is, you're going to use P, and you occasionally will eventually want to use Q, but Q is a little bit more esoteric. Yes?
Is R to take like samples from that population, or what would I use it for?
Yes, R is to take random numbers from that distribution. So for example, here's what I'm going to do. I'm going to say, let's just use it interactively. I'm going to say I'm going to take random samples from a Gaussian. NORM is norm, short for normal. Give me 100 draws. Okay, so there's 100 random samples from a normal distribution. I didn't tell it anything, so it had better have some defaults. Or if I can spell, you'll see at the bottom of the page, it'll say, okay, here are the arguments. You need to tell me how many draws you want. And if you don't tell me what the mean is, I'm going to say the mean of the distribution is 0. And if you don't tell me what its variance is, I'm going to say that the variance is 1. I could have changed those things if I wanted 100 draws from a noisier distribution or a distribution centered somewhere else. Okay? So there are a bunch of different distributions. This is one that Kobe will want you to see. If I want draws from an exponential distribution, again, 100 draws from a different distribution now. REXP, there's 100 draws from a different distribution. If the Gaussian looks like a snake that swallowed a hat, the exponential is this nice distribution that sometimes we say is memoryless. Has sort of the same constant shape no matter where you look at it from, and it's one-sided. Okay, a binomial distribution is also pretty useful. You'll see in the code that I have an example of draws from a binomial distribution. So I'm going to construct some variables. A is going to be true, false. X is going to be a bunch of draws from a normal. Y is going to be a bunch of draws from a binomial. So that's just zeros and ones with a probability of being a 1 of 0.3. Again, n draws from that. And then Z is going to be something completely different. It's going to be a bunch of characters. AA, BB, CC, CC, DD. So a bunch of different types. Booleans, bunch of floats, doubles, and some character data. And then if I want to put them all together into a thing, I can't put them into a matrix. Matrices only accept numbers. I'm going to put them into a data frame. And so to build a data frame, I just say A, X, Y, Z, B, C. are going to go into my data frame. I'm going to build my data frame. If I download a data set and convert it into the R format, almost certainly your conversion utility is going to give you a data frame. Okay. All right. So let's take a look at what that data frame looks like. Let's run this code. It doesn't like something. Size is missing, so I needed to add that in. Inside our binom, I'm going to say size is equal to 1. That means I only want one draw from a binomial, so as to make it a Bernoulli. Okay, so here's my data frame. Again, it's got rows, it's got columns. Something that's slightly different about a data frame is that the columns might have column numbers, but they also have names. So I put objects into my data frame called A, which was a bunch of true falses, and that column got a name. Matrices don't have column names, or if they do, they're not nearly as useful. Data frames do. So these are much closer to data sets, where the variables, the columns in the data set have names, and you might say, I want to look at the male, the gender variable. And you might not know where it is, but you want to access it, query it by its name. Data frames can be queried by names, whereas arrays are only queried by their column numbers. Okay? And I've put a bunch of different types side by side into the same construct. Okay? Notice, what did I do? I did a couple of crazy things when I constructed this. For example, I threw in B and C. B and C were things that I constructed way up the code, and they were just scalars. B was a 7, C was an 11. Actually, these were constructed in that function example that I skipped over today. But they're just scalars. And much like when I was constructing matrices, I've only got one number, but I got to fill 20 rows with it. It just recycled them. Same thing with this character vector. If the character vector was only of length 4, So when I put it into my data frame, it just decided, okay, fine, I'll just recycle it. So check to see the things that you're putting together into a data frame. If they're of different lengths, you might not get the data set you were expecting. Okay?
So, Jay?
Yeah.
So defining the variable C doesn't run over the function C?
It would if there was a function C. Is there a function C?
The concatenate. To create-
Oh, no, because that's reserved. So we're fine.
Oh,
Yes,
because it's reserved.
yes.
But in general it would.
You can't run over base functions, but you could run over another function that's lower in the scoping rules. And when we get back to functions, I did skip functions today because there are a lot of little quirks of functions we need to talk about, and one of them is the lexical scoping that it uses. That's it. But that's a good point. Yeah, it's not there are very few reserved words that you can't write over. Okay. So here's my data set. I just printed my data set. Take a look at this stuff that's commented out, and you might want to enter some of these in yourself. Just like when we were dealing with matrices, it's often going to be the case that we just want sub-matrices of the data frame. We don't want the whole thing. We don't want to print the whole thing to the screen. I just need some pieces of it. I need these variables. I only need these rows. I only need the rows for which this condition or this query happens to be true. Okay, so many of the same subsetting rules we used in matrices, the same notation will work on data frames. So for example, I can say I want the first through third rows, but what I can also do that I couldn't do with matrices is I can start to use the column names. I can use the names of the variables as if those mean something. So the $sign is the way that I represent the name of something. So these are all commented out, but I'm going to do them. You can copy some of them into your code, or you can follow along. I've got this thing that I just constructed called my data. If I say I want my data, notice in the code I've been well behaved and always said print something. But if I ask for something at the command line and didn't give it a function, it's going to assume, you probably just wanted me to print it to the screen. Okay? So if I print my data sign $A, that's going to say go into the data frame, my data, and find the thing that has the name. That's probably the simplest way right now to read the $sign, the thing that has the name A. So there's my true falses, true falses. Something very strange just happened here. Anybody want to pick up on what just happened? I asked for a column of a data frame. Data frames have rows and columns. Okay? What did it give me back? It didn't give me back a one-column data frame. It said, look, that's a one-column data frame, but a one-column data frame is basically a vector. So I'll give you back a vector. It just recast the object for me from data frame to vector. And that's fine because that's probably what I want. If I just want one column out of a data set, maybe I'm happy using a vector. But if I then supply that to a function that was expecting a data frame, I'm in trouble. So recasting, as I said, the loose typing in R, the way that you can always swap the typing, the functions can do unexpected things to you sometimes. Sometimes you have to explicitly tell them, make sure whatever you give me is of this type. Okay? That's a little example where I pulled out something, I pulled out a piece of a data frame and it gave it to me as a vector because it figured I probably wanted it that way. So I can call things by their name. I can call things, as we did with matrices, by their positions. So what would this be? 2:5, 6. Does that exist? 1, 2, 3. Yes, it does. But it's not very interesting. 4. What would that be? This would be the second through fifth rows and the fourth column of this matrix. So that's going to be a little piece of the matrix right here. If I'd said 4 and 5, now it'll give me a data frame because it can't reduce it in scope. It can't recast it as a vector. So it's going to give me a little piece of a data frame. Does that make sense? I can also, in these hard brackets, if I'm using a data frame, I can use variable names. So I can get, this is the second through fifth rows of the 8th variable. Okay, and that goes into, that works for me. That's pieces of that first row. I can also use that C variable for concatenation inside my subsetting. So this is what? This is the second through fifth rows of A variable and X variable concatenated together. Okay, so here you go. A and X, 2 through 5. If I wanted 2 through 5 and 7, Okay, I'd have to use concatenation again, and I could say concatenate the sequence 2 and 5 together with the 7, and there's your submatrix. Okay, so that's how to play around with data frames. I did not talk about functions today, but they do have enough quirks that we'll get to, that we'll use. That will be the first thing we talk about on Monday. For those of you who want to, I don't actually know when we're talking on Monday. Is it 10?
Oh, I have the schedule up.
Yes.
Sounds right.
I will talk for an hour on R, and then Vishesh will talk for an hour on statistical methods with R used as illustrations. If people want to, 10 o'clock. MD?
MD 221.
Okay, so across, stretch your legs if you've not been to MD. For those of you who are Dustin students, if you want to see that.
MD is Maxwell Dworkin.
Yeah.
33 Oxford Street.
It's that way. Just ask people for MD. Everyone knows where it is. Kobe wanted you to know how to draw from distributions in order to be able to do the assignment that he's going to give you on Friday. Okay, so we've briefly touched on the R function, which is how I get random draws from a distribution. We'll look on Monday at this other piece of code, dpqr. You can run that though if you've already downloaded it. Run it. It'll illustrate in 4 different panels what the different meanings are of these 4 ways to access a distribution. There's not a Laplace distribution in R, in the base package of R. There is, however, we've already seen it today, an exponential distribution and a binomial distribution. So binomial can, or the binomial size 1 is a Bernoulli. So you can get a 0, 1 draw from a Bernoulli, and you can get an exponential distribution. And when Kobe explains to you the Laplace is a double exponential, you could think about how can I construct my own Laplace from the combination of a Bernoulli or a Laplace, and that'll just make this not a trivial one-line problem for you when he asks you to add Laplace noise to certain things. Okay. Any questions so far, or actually any questions at all? Okay. We'll cover building functions then. And one last type in R called the list, which is a way of storing multiple things that have different types, not in a rectangular format, but in a less ordered format. But they behave very much like data frames on Monday. And then we'll start talking about plotting. And R is, as I said before in the intro, got a lot of flexibility, used a lot for plotting, but it does have its own sort of arcane set of rules that you just sort of have to learn. There's a lot of logic to the language of R, even if it's unique to R. There's not necessarily a lot of logic to the plotting commands in R, even though they're reasonably powerful. You just sort of learn by example in terms of plotting. Okay, so finding something that looks a lot like what you want and then tailoring it, or reusing code you've had before, or reusing examples that we give you is really the way to learn the power of R plotting if you're doing R plotting. Okay. Any other questions? Great. Okay. I'll see many of you on Monday at 10, and let me if things come up before then you already need help on, feel free to send me an email, and if you know what my email address is, and I will and I'll answer. Okay. Great. Anybody else need sign this thing?
Everyone knows the schedule for tomorrow. So tomorrow is mainly open for midday